Okay, today we're going to cover logarithms and exponents. So this is the last section of functions. So we start with the exponential function. So it's written kind of different, weird. Uh, I see it. I've never seen this type of way that it's expressing an exponential, but let's go through it. So pretty much an exponential function is written as a function going from the real numbers to the real numbers but positive, and it's written as the exponential base x equals b to the x, where b is a positive real number and b cannot equal 1. The parameters b is called the base. That's the base. That's the base. In the expression b to the x, the input x to the function is called the exponent. All right, so let's review our properties of exponents. So as you all recall, if you have a base b raised to the x times base b raised to the y, we add the exponents, keeping the base. Here we have b to the x and the whole expression is raised to the y power. We multiply the exponents, x times y. If we divide base x raised to the x divided by base raised to the y, we subtract. And if we have two variables raised to the x, b variable and a constant raised to the x, it's b to the x times the new constant. So these are the properties that we have used in college algebra and pre-cal, and so we apply them again just to review. All right, so let's figure out how to do this one. So participation activity, we need to match to see which one of these match with the blues. So for the first one, it's bk plus 2 as the exponent. So that means plus means times. So this can be written as bk times, sorry, not bk, 2 to the k times 2 to the second power. So 2 to the second power is 4. So it has to be this one. Yep. The next one is 2 raised to the k plus 1 divided by 2k minus 1. Since we are dividing, that means subtract. So I'm going to do k plus 1 minus k minus 1. So two negatives make a positive. So that should be, the k's disappear. So that should be 2 to the second power, which is 4. Yep. There's the negative being distributed. 2 to the k, we're using the property where we multiply, it's raised to the second power. So this should be 2 raised to the 2k. So this one should be third. That is correct. This one is 4 times 2 to the k. I can express 4 as 2 squared, and that's 2 to the first. So 2 to the second power times 2 to the first, that's 2 to the third. So 2 to the third times k should be that one. And the last one, I have to distribute the 3. So that would be 3k plus 3. So that's 2 raised to the 3k plus 3. Awesome. Challenge activities. Let's go through these. So let's start. Notice I have the same bases. I have my exponents. I have to add. So that should be a 9. Yep. Next one, I have same bases. I'm dividing. Division means subtract. So 15 minus 4 is 11. 711. Next one, I have an exponent raised to a power, so I have to multiply the exponents. So that should be 72. Next one, they want us to write that as a product of two bases. So I'm thinking that might have to be a 7. Is that correct? Tis. Next, 5 to the 6th power times 5 to the 9th power. I gotta add those. So that is 15. 15, 5 to the 15 divided by 5 to the 4th. I gotta subtract, so that should be 11. Awesome. Okay, now the logs. The exponential function is 1 to 1 and on to, and therefore it has an inverse. So in order for it to have an inverse, its inverse is going to be the logarithmic function. That is the inverse of the exponential. So it is going from the positive real numbers because logs don't work for negatives. So it has to start with positives and it goes to any real number. So we can convert from exponent to log. Here's our base is b, x is the power, there's the result. If I convert it to log, it is written as log base b, the b goes as the index. The solution is y and it equals to the power. So converting from exponential to log is written in that format. So the parameter b is called the base of the log. That's the base. Graphically, this is the graph of an exponent function. So it goes from negative all the way up. Notice that there is an asymptote. It does not cross the x-axis, so it gets really close. So if you have taken chemistry, I mean not chemistry, you have taken calculus, we know that that graph just goes on to infinity. So it never crosses this line of the axis of x. It's an asymptote. This axis is an asymptote. The log function, the graph of that is going to be reversed. So it starts, it doesn't cross the y-axis. It starts from 0 and it just goes on to infinity. So that's the graph of the log. It's kind of like here's the L and it's just going reversed. So here are the properties for logarithms. So if you have a log base b of x times y, remember times means plus. So we can write it as log base bx plus log base b of y. As you recall from the exponentials, division means subtract. So log base b of x divided by y is log base bx minus log base b of y. The third formula is log base b x raised to the y power. So what happens is, since this is the x is being raised to a power, we move that power to the front. So it becomes y times log base bx. The last one, we use in case your calculator does not have a change of base formula. This is called a change of base. Your calculator may not have the function to compute logs with a different base other than ln or base 10 or an e. So because if you don't have that function in your calculator, we use what they call a change of base formula. So what you do is you write it as log base b of x divided by log base b of c. And the bases you need to make sure that the bases are the same. So you can use base 10s or ln, which is log base e. Regardless of what you do, it should give you the same result. And just make sure that your c is not equal to 1, but otherwise you're going to get undefined. So here are your bases, here are your formulas for the logarithms functions. All right, so let's go through the exercises. Let's do a participation activity. I have log base 3 of 10 plus log base 3 of 100. So what I can do is I can write 100 as 10 to the second power and move that 2 to the front. So that way I can get, let's see, what do I get? What do I get? Base 10, that's 2, 2, 10. This should be log base. Huh, that's a tough one. That means times. So that should be, oh, that's right. Log base 3, it should be, so it's 10 times 100 is 1,000. So this should be first one. Second one, it's going to be log base 3 of 1,000 minus log base 3 of 100. Minus means divide, so I'm going to divide 1,000 by 100. So that should give me log base 3 of 10. Yep. This one is 2 log base 3 of 10. I'm going to move the 2 in the front and the top of the corner of the 10. So that should be 10 to the second power, which is 100. So that should be this one. This one is log base 3 of 10 over log base 3 of 2. I'm going to use a change of base. So this one could be used for the change of base. It's going to be log base 2 of 10 using the change of base formula. This one is calculating, well, I can change 1,000 to 10 raised to the third, and the 3 goes in the front. Therefore, if I have 3 log base 10 of 10, log 10 of 10 is going to be 1, so it has to be 3. Yep. Or you can convert it. Awesome. All right, so time to do the challenge activities. Let's start them off. Log base 4 of 5 plus log base 4 of 9. Add means multiply, so that should be log base 4 of 45. Okay, next. Log base 2 of 48 minus log base 2 of 8. Subtract means divide, so 48 divided by 8 is 6. This one is log base 2, 64. So it looks like they converted 64 having a base of 4. So what do I raise 4 to get 64? Is it 3 or 2? I think it's going to be 3. So let's see. It would be a 3. Let's check. That is correct. 4 raised to the third is 64. So I move the 3 in the front. Therefore, it becomes 3 log base 2 of 4. All right. Log base 2 of 9. I believe they're using the change of base. They want to change into base 5s. So that means the 9 goes on top and 2 goes on the bottom. Yep. See, like I said, remember when we use the change of base formula, we can use whatever base you want as long as they are the same, but we use the result and the base there. All right, so I have log base 3, 7 plus log base 3, 12 minus log base 3 of 4. So plus means to multiply, so that would be 84. So 84 divided by 4 should be 21, I think. Yes. All right, last one, log base 8 of 6 minus log base 8 of 3 plus log base 8 of 6. So minus means to divide. So 6 divided by 3 is 2. Then I'm going to multiply 2 times 6 is 12. So they want to keep the bases the same. So that would be 12 and 8. Yeah, cool. They did it different. Look at that. They did they did this first. They they subtract means divide. That's what did they do? 6 times 3. What? They grouped the positives together. So 6 plus 6 is 12. That's 6 plus 6 plus log base 8 6 plus log base 8 6. Add means to multiply. So there's the 6 times 6, that's 12. No, that's 36. And then you have a 3. So 36 by 3 is 12. And then they did the change of base. Okay, that's fine. So tomato, tomato. All right, so a function is said to be strictly increasing if whenever x1 is less than x2, then the function evaluated x1 is also going to be less than the function evaluated x2. It is considered to be strictly decreasing whenever x1 is less than x2, then the function evaluated at x1 is greater than the function evaluated at x2. Therefore, if b is greater than 1, then the functions f of x equal bx and f of x equals log base b of x are both strictly increasing. The fact that both functions are strictly increasing can help approximate the values of the function. So if you do not have a calculator and we want to determine the results of certain things, we can use certain facts. So on the bottom here, we have all the facts of base 2s. So they calculated all the base 2s. So 2 to the second is 4, 2 to the fifth is 32, 2 to the eighth is 2 to 56, 2 to the third is 8, and so forth, right? So they calculated those. And so we can approximate what the value is at certain logs with different bases. Well, in this case, they're bases of 2. That's why we have all the bases of 2, so we can evaluate it. So all we have to do is just look for the log base 2, they all have 2s, of 64. And so all we have to do is just find what the result is and figure out what the exponent is. So in this case, it is a 6. 2 to the 6 is 64. So therefore, log base 2 of 64 has to be 6. Log base 2 of 100. So notice that in this expression here, I have ceiling. So what we're going to do is we're going to locate the value that's close to or in between, or what's closest to 100 with a base 2. And then since it's a ceiling, we're going to go with the bigger one. So let's see, 2 to what power gives us close to 100? So we know that it's going to be pretty much between 64 and 128. So it's got to be 7. So I know it has to be in between 6 and 7. So since it's a ceiling, I say it's a 7. Yep. All right. So this one, the next one, number 3, we're looking for floor. I want to find a base containing some exponent that gives us close to 927. Well, 927 is between 9 and 10. So we want to do the floor. So it has to be the smaller one. So it has to be 9. What is the value of the smallest power of 2 that is greater than 2 to the 9.2? The power of 2 is a number that can be expressed as 2 to the k, where k is a non-negative integer. So that one would be 1024. So 1024. I want the value of the smallest power x that is greater than 2 to the 9.2. Well, 9.2, it has to be 10. 10 has to be greater than 9.2, so it has to be 1024. All right. So the growth of population is often modeled mathematically by an exponential function. So we consider examples in which population of lizards on an island at the beginning of a study is denoted by a number p. After a time period of t days, the population is described by the function lizard of t equals p times b to the t for some number b. The number of lizards on the island must be an integer, but the function lizt will map positive real numbers to positive real numbers. It's understood that the population models are approximate and that the true population at the time t will be an integer that is close to liz of t. The number b indicates how fast the population of lizards is increasing. Therefore, the value of b will depend on the conditions on the island and the characteristics of the lizards. Developing a good mathematical model for population growth, finding the accurate function lizt would likely require significant field work and study, but one such model was developed. It would be possible to answer questions such as approximately how many days will it take until the population of lizards reaches n? So the value of t that satisfies that equation is going to be n equals p times b to the t. That implies that n over p is equal to bt. So what they did was they divided both sides by p. There's your expression. Therefore, if I write this in log format, my answer is going to be log base b of n over p is equal to t. And that's how they calculate t. In computer science, we use a function that is used when we calculate certain things. So it's called divide and conquer. You may run into it later on when you all take higher levels of computer science. This divide and conquer technique is a common strategy in computer science in which problems are solved for a large set of items by dividing the set of items into evenly sized groups, solving the problem on each half, and then combining the solutions for the two halves. So for example, one approach to sorting a list of numbers, which you all have done in Computer Programming 3, where a list of numbers is divided, it divides the list in half, and then you sort each half separately and then merge the two sorted sets. The logarithm function plays an important role in analyzing divide and conquer algorithms. So consider this simpler scenario. So Ingrid has a bag of chocolates. Let's just say there's n chocolates. So the bag is not empty. So we can't let n has to be greater than 0, so it can't be empty. So Ingrid meets a friend and decides to split her chocolates into 2 evenly sized piles. And she gives her friend the chocolates in one of the piles and then puts the rest in her bag. Then she meets another friend and splits her chocolates again. And every time she meets a friend, she keeps doing this process where she gets half, gives it to her friend, puts the other half in the bag. And she continues to do that on and on and on. So how many friends can she meet and share half her chocolates before she is down to 1 chocolate in her bag? That's where the divide and conquer comes into play. So there is an ambiguity in the problem of Ingrid and her chocolates, which requires clarification. So if Ingrid has an odd number of chocolates, it can't not be divided evenly. So if Ingrid has 17 chocolates, she will have to divide them into 1 pile with 8 in one pile and 9 in the other. So in general, if there are n chocolates with 1 pile having n over 2, and notice it's a ceiling, and the other pile will have n over 2, which is the floor. Does Ingrid keep the bigger or the smaller pile for herself? Well, that just depends. Does the choice of the pile she chooses affect the number of friends with whom she can divide her pile? Well, let's investigate it. It should. It should. So let's check this out. Let's do this one. So let's say that she has 8 chocolates. So she divides the pile into 2 groups. Each group has 8. So she keeps half, right? She keeps half and then gives the other half to her friend. So now she's got 4. She divides it out again. She keeps 2, gives the other half to her friend. Now she has 2. She cuts it again in half. She keeps 1. Her friend has 1. So how many times is that? 3 times. 1, 2, 3, and then she has her 1 chocolate left. So she had to divide her pile 3 times. All right, let's try another one. Suppose she has 7 chocolates. Well, she's going to divide it out. So she will keep uh, 3 and give 4 to her friend. Now she's got 3, so she splits it. All right, so now she gives 2 to her friend and she has 1 left. Well, there's her 1. How many times did it take? The process took 2 steps. So that took 2. So notice, this one required 3. This one required 2. Now let's do it the other way. What if she keeps the 4, right? And she gives 3 to her friend. Well, if she keeps the 4, now she can split it up. She'll give 2 to her friend and 2 to herself. She splits it again. She gives 1 to her friend, keeps 1 to herself. We have 1. Notice the process took 1, 2, 3. It took 3 steps. So it does make a difference whether or not she gives the bigger pile or she keeps the bigger pile. Right? So this happens, if it happens that the number of chocolates in Ingrid's bag is a power of 2 for non-negative integers, then every time she meets a friend, the chocolate can be divided into 2 piles. She starts with 2 to the k chocolates. After meeting the first friend, she's down to 2 to the k over k, which is 2k minus 1 chocolates. After the next friend, she's down to 2 to the k minus 1 over 2. It goes 2 raised to the k minus 2, and she keeps on going. Each time she meets a friend, the exponent of the number of chocolates goes down by 1 until she is down to 1, which is 2 to the 0 chocolates. She starts with 2 to the k, and she wants to wind up with 2 to the 0 chocolates. The number of friends she can meet is then computed by k equals 2 log base 2 to the nth. If n is not a power of 2, then log base 2n is not an integer. Certainly, the number of encounters with friends has to be an integer. Also, n is not a power of 2. Ingrid will be forced to divide her pile unevenly at some point in the process, right? Of course, she'll have to keep, either she'll keep the one with the most or she'll give one with the least. Either way. So if Ingrid always takes the larger half, then the number of times she can divide her pile of chocolates in half is log base 2 to the n, and notice this is a ceiling. If she always takes the smaller half, then the number of times she can divide the pile of chocolates in half is also log base 2 to the n, but it's now the floor. So there's a theorem that corresponds to that event. So let n and b be positive integers with b being greater than 0. Consider a process in which in each step n is replaced with n over b until n is smaller than b. The process lasts for log base b n floor steps. If instead in each step n is replaced with n over b with the ceiling until n is smaller than b, the process lasts for log base bn ceiling steps. All right, so let's take a look at the participation activity. So suppose that Ingrid starts with 54 chocolates. In each step, she divides the chocolate into 2 piles as evenly as possible. If the piles cannot be divided perfectly even, then she always takes the larger pile. Okay, so she's going to keep the larger pile. Interesting. All right, so how many times can Ingrid divide her pile? All right, so since there are 54, divided by 2, there's going to be 27 in each. Right, so 27. So that would be, so 54 is even, so I'm going to use my formula that's here, which was, where was it at? Where was it at? I lost it. Oh, log, there it is. Log base 2n, and this would be ceiling. So what is log base 2 ceiling? I want to get as close as to 54. So what do I have to raise 2 to get 54? I'm going to say 6. No, that's 64. I went too high. What's 2 raised to the 5th? That's 32. So 2 to the 6th is 64. 2 to the 5th is 32. 54 is in between. So since I'm doing ceiling, it has to be 6. All right, suppose that Ingrid has 27 chocolates in every step. She meets 2 friends, and she divides her pile 3 ways between herself and her 2 friends. How many steps until she is down to 1 chocolate? All right, 3. All right, so I think this is going to be log base 3 of 27. So that should be 3. I think it should be even. Yep. All right. Suppose that Ingrid has 63 chocolates. In every step, she meets 2 friends. She divides her pile 3 ways between herself and 2 friends. She divides the chocolate as evenly as possible, but in the event that the chocolates cannot be divided perfectly evenly into 3 piles, she's going to take the larger pile for herself. All right, so all right, so that's going to be a ceiling. So that should be log base 3 of 63. So I need to figure out 3 to what power gives me close to 63. Well, 4 is 81. I think that's a little bit too high. 3 to the 3rd is 27. So 63 is between 81 and 27. 3 to the 4th is 81. 3 to the 3rd is 27. Somewhere in between. And so she said she's going to keep the pile for herself. So that would be a ceiling. So ceiling has to be 4. Yep. Nice. All right, additional exercises. All right, so let's take a look at these. So what do we do when we have 6? I'm showing you the answers. Let's take them off. Well, we should just leave them on there. That's right. You can see them. All right, so I know that you have a power 6 to the exponent k raised to the k. I know I have to multiply them, so that should be k squared. This one, I am multiplying 2k to the third. That should be 6 raised to the 6k. This one should be, I'm multiplying, so I believe this should be 6, 2 to the k plus 1. Yes. This one I'm going to be subtracting, so it'll be 2k minus 1 plus k. So that should be 6k minus 1. Oh, sorry, that should be, because the negatives make a negative and a negative make a positive, so I'm sorry, that should be 2k plus another k minus 1, so that should be 6 raised to the 3k minus 1. Yep. This one I'm subtracting. There's a 1 located there, so this should be 6 raised to the 2k minus 1. F, I can rewrite 36 as 6 to the second power. So second and the k I have to add, so that should be 6k plus 2. There should be a 1, so that should be 6k squared plus 1. Cool, cool, cool. Exponents, the logs. Let's take a look at the logs. Let's go over the logs. Same bases. So that should be log base 5 of 2k. 2 goes in the top. Log base 5 k squared. Minus means divide. Log base 5 k over 7. This one I'm going to use change of base. Log base k, log base 5 of k. I can rewrite this as 5 squared. 5 squared. Let's see. 5 squared. That can be 5 squared. They have the same bases, so I guess it's I don't know. 2 goes in front. 2 log base 3k. I can rewrite this as 5 squared. 2 goes in front. The 2's go away. Therefore, I have this component. Oh, that's a change of base. So that becomes that. Very interesting. All right. For each expression, give an equivalent expression that does not use log function. Okay. So, oh, I see. So if you have a base and you have a log with a base the same, these two cancel out each other, which gives you x. This one we can rewrite this as 2 to the second. Yeah, there should be 2 to the second. That 2 goes in the corner. So 2 and log base 2 go away. So that way you're left with x squared. This one is, I can rewrite 4 as 2 squared. Square, let me think. That's an interesting one. Well, I can rewrite 4 as square root of 2. That's an interesting one. It got me. That should be a half. 2. Yeah, that should be a half. Because if we take the square root of 4, that's 2, and you put the 1/2 there. So 2 log base 2, and that half right there. So that should be x to the 1/2 is square root of x. That was a tough one. All right, last two. If we have this table with all of our exponents bases of 3, and I want to approximate these. All right, so 189. 189 is between 81, 280, 243. I'm doing ceiling, so that should be 5. I need 536. 536 is in between there. I'm doing floor, so that should be to the 5th. Log base 3 of 2. 2 falls right in between. I'm doing floor, so that should be 0. Log base 3 of 55. 55 is between 2781. It's 3 and 4. I'm doing ceiling. That should be a 4. Awesome. And that should be it. Hope this was very helpful for y'all, and that should do it for this section.